So let's take a look at some review stuff, review topics, just for a minute, just to help orient ourselves as to where we're going in this section. And remind ourselves of some notation. What notation do we use for this, sample mean?
X bar.
X bar. Excellent. Thanks, Jacqueline. Someone else. How about the population parameter? What's mu? Good. Couldn't even get it out, and you've already got it. Oh, excellent. Sample standard deviation.
S.
S. Nice. Somebody else now.
Sigma.
Sigma. Well done. Population or sample proportion.
Yeah.
P hat. And then population parameter. Just P. Good. Now what we're hoping for is that these are good estimates of these. So we don't know exactly what the mean is in most cases, but we're going to use these as estimates. And in fact, a lot of times you'll hear these things called point estimates. So this one estimates. This one. And this one estimates. This one. And finally, the sample proportion estimates the population proportion. Typically speaking, we don't know what those values are. So this is your best guess. And in as much as that's your best guess, a lot of times we'll call that a point estimate. Point estimate. So you hear that referred to in the book because it's just one value. It's just one point. But you know going into any kind of sampling situation that your sample estimate, whatever it is probably not going to be accurate. It's probably not going to be spot on. So you surround it by a confidence interval. Now, we did section 7.1, which was confidence intervals for a population proportion, for P. Now we're here in section 7.2. We're going to do population, or confidence intervals for a population mean. Section 7.3, that's going to be here. Now, there's a couple ways you can form a confidence interval for a population mean. It kind of depends on your situation. For the most part, it's going to boil down to a t-distribution. We practiced the t-distribution the other day on Wednesday, but we're going to use it today, at least implicitly. So your confidence interval for mu, how you create that is going to kind of depend on what you've got. So the first question you have to ask of your data, is it normally distributed? If it is, great, then you've got a follow-up question. If it's normally distributed, do you know what sigma is? Well, if you do, again, great. If you do, both of these questions are yes, then you're going to use a z distribution. What about if you don't know what sigma is? So your data does come from a normal distribution, but you don't know what the standard deviation is. Well, then you're going to use a t distribution. So that kind of thing can happen. You have normal data, but you don't know what sigma is. That's fine. How about working down the other path? If you don't have a normally distributed set of data, but your sample size is, somewhere bigger than 30, then again, you're going to use a t distribution. What about if you don't have normal distributed data and you don't have a sample size greater than 30? That's where you're going to have to use a non-parametric method or bootstrapping. Now I'm going to add this to this course. That's going to be section 7.4. We'll talk about that on Wednesday. But let me look back here for just a moment at this one, the z distribution. To get here, you got to follow this path. You got to follow a yes, then a yes. And that actually requires that you have a really strange situation. Remember, mu is the population mean. So if we're finding a confidence interval for mean, then confidence interval for mu, that means we don't know what this is. We're trying to estimate it. And it just seems weird to me that somehow you would know mu, excuse me, not know mu, but know sigma. How is it that you have the standard deviation for the entire population and yet not know what the mean is? It's just really unlikely to happen. So we'll probably never really use this. I mean, I'm sure that if you wanted to get creative, you could write a problem that you would use the z distribution. So hardly ever use. So it's more likely that you're going to end up with a t distribution. That is, you have normally distributed data, but you don't know what sigma is, in which case you're going to use a t distribution. By the way, do you remember how many degrees of freedom are associated with your t distribution?
-1.
Yeah, so your degrees of freedom is going to be n minus 1, where n, what's n in this case? What's n all about? What's that n represent? Sample size. All right, so you can end up with a t distribution that way, or if your sample size is greater than 30, even if you don't have normally distributed data to begin with, if your sample size is greater than 30, then again, you can use a t distribution in creating your confidence interval. So again, your degrees of freedom is going to be n minus 1. That's fine. And well, if you answer no and no, you're kind of stuck. Now you're going to be stuck doing non-parametric method. That's going to be discussed at the very end of the course. Bootstrapping will be this Wednesday. But that's where we're at. We have to figure those things out. Now, our confidence interval for a population mean is going to look like this. It's going to look like x bar plus or minus e. X bar, that's your point estimate. That's our best guess as to what the true mean is. But we know it's not going to be exactly right. So we surround it by a confidence interval, so that's your best guess. That e, that plus or minus e term, looks like this. E equals t sub alpha over 2 times s over the square root of n. The good news is that because we're using StatDisk, you're not actually going to have to get your hands dirty in a lot of this calculation. This is kind of a pain. You have to know what alpha is. That comes from your level of confidence. Find t sub alpha over 2, then multiply by s, the sample standard deviation divided by the square root of sample size. There's a fair amount of work that goes into that. But like last section, I'm going to put the emphasis on you knowing how to state your conclusions. So that's kind of a little bit of where we've been and where we're headed. Let's actually practice some examples. So let's see, statistics, section 7.1, example A. Here are summary statistics for randomly selected weights of newborn girls. Now, I like to start these problems by writing down the things that I think I'll need. So right away I see that there's n equals 157. X bar is kind of strange. It's 30.8 Hg, which is not millimeters of mercury in this case. It's actually hectograms, which is a really strange unit to use. Whatever. It's 3,800 or 3,080 grams. The standard deviation is S is 6.2 hectograms. And it asks us to construct a confidence interval estimate. It says use a 95% confidence level. So I'll write that down as well, 95% confidence level. Does anyone remember what that would make alpha? What value that would give for alpha? Yeah, it's going to be 1 minus 0.95 or 0.05 or 5%. You know, whatever works for you. Let's look back at our chart. Now, I'm not always very good at demonstrating this and modeling this, but I'm trying to get better. You got to kind of check your assumptions and see where we're at. Did it say anything in the problem about having a normally distributed population?
No.
No. So we're branching down here. Is our sample size greater than 100, greater than 30?
Yeah.
Yeah. So we're going to use a t-distribution. Now that kind of stuff is more or less built into the software for you, but you should be aware that you're using a t-distribution. The other knock, yeah, please. I fixed it. Text back and check with me again. Okay, so let's keep going. The thing about this, the t-distribution is that it starts to look a lot like the z-distribution. We saw that the other day. Let's see, t or z, where is it? Thought I had that on Desmos someplace. Let me see if I can't pull it up. I signed in it, yes. Yeah, here we go. So this was our t-distribution and z-distribution comparison. And when n equals 1, that is, you have 1 degree of freedom, there's a noticeable gap between these two distributions. But as your degrees of freedom increases, there's not much of a difference between the t and a z. And at about 30 degrees of freedom, they're really close. Now, it used to be that our tables would cut off at 30 degrees of freedom. So that's part of the reason for this. Nowadays, our technology is great. We can do t-distributions for any degrees of freedom. It's really not much need in this case to use a z-distribution. All right, let's go on and finish this one up. We want a 95% confidence interval. We're going to do that in StatDisk. So if you got some data there already, you can clear that out. Somehow I think I want to keep that around for next section. So let me just paste it in here and return back. Let's clear that out. Go to analysis. Is there anything from the analysis menu that looks like it might be helpful?
Confidence intervals.
Confidence intervals. We don't want to do a one proportion confidence interval anymore. That was section 7.1. We're going to do a mean one sample. So mean one sample. Let's click that. That's underneath the analysis menu. Then confidence intervals, mean one sample. Level of confidence, 95%. Looking good. What was our sample size? 157. Good, so let's type that in, 157. The sample mean was 30.8 hectograms. I still find that an interesting choice. 6.2 was the standard deviation. Now I put that in for S. Should I have put it in for sigma?
No.
Well, 6.2 is the standard deviation. But how come I'm putting it in for S and not for sigma?
Because it's for a sample and not a parameter.
Excellent. Perfect. Spot on. It's because 6.2 is for a sample. It's not a parameter. We don't know what the population standard deviation is, but we do know what the sample standard deviation was. So that's why we're putting it in here. And this is the nice part. This used to be like 5 minutes of work back in the day when I was teaching this just out of a book with a simple calculator. There you go. Bam. So our confidence interval is between 29.8 and 31.77. So let's write that down. So our 95% confidence interval, 95% confidence interval is 29.8226. Is less than something, is less than 31.7774. Now my question to you is, what notation, what should I put in the middle? What are we trying to find a confidence interval for?
Parameter.
Yeah, you should always put a parameter in here. In this case, which parameter should I use?
U.
Mu. Nice. Nice. So, all right. The last part of this is to write your conclusion in words. So if you're going to write your conclusion in words, we're going to write it pretty much the same way we did with population proportions. We can be 95% confident that the true mean, now this is birth weight of girls, true mean birth weight of girls is between 29.8226 and 31.7774 hectograms. Now, I'm probably not going to ask that you write down 4 digits of accuracy like that. I don't think that our scales are really that accurate. That would be like 1/100th of a gram, and that's just ridiculous. So it's too small to really worry about. So maybe 29.82 and 31.78, those are fine. All right, looking good on that one. Comments or questions on this first one? There's a couple things that I want to see from you on this. I want to see the word true. That's kind of a polite way, without getting mired in statistical speak. It's a polite way of saying we're estimating the parameter, the true population mean. We don't know what it is, but we're estimating it. And the other thing I like to see is a description of what that is. I don't want some bland statement saying our confidence interval is between this and this. That's not going to get you a lot of points on an exam. What is going to get you points is stating this correctly, mention the true value of the parameter, and describe what that is in words. I've made this calculation a lot easier on you, so I'm asking for a little bit on the back end. I want the notation done right. All right, again, reaching out. Anything on this one bothering you still, or something?
Where is the 5% like necessary?
Great question. So what you don't see that's going on behind the lines is this. Your confidence interval has this form. It's going to be x bar plus or minus e. E has the form of t sub alpha over 2, where n minus 1 degrees of freedom, times s over the square root of n. So alpha is the 5%.
Yeah.
That puts you at a place out in the right tail of the t-distribution so that you can get this number.
Yep.
And then you multiply by the standard deviation divided by the square root of n. That gives you your error term. This down here, this is your x bar minus e, and this is your x bar plus e. So in direct answer to your question, that alpha comes into play in getting your t-value.
Okay, so even though we're not going through all the steps, we should still acknowledge it and write it down?
It's not a bad idea to keep track of your significance level and your confidence level. This is your significance level.
All right.
Yep. Thank you. Anything else? I'm trying to think if there's a follow-up question to this part, or example A or not. Let's see. Was there? Example A. Are those results very different from the confidence interval of 30.1 to 32.1 with only 18 sample values and a different sample mean? All right, so let's take a look at that part. Let me draw this. Let's see, so. Let's see. Versus 30.1, and I got to copy this down first. Give me a second. 32.1. So. All right, so we're going to compare this to this confidence interval and see what we see. So our confidence interval, let's do this. So I'll make that 29. 30, 29, 31, 32, 31. All right, so just giving myself a little number line to work with. So our first confidence interval for this one was between 29.8, so that's roughly here, to 31.77, so 31.8. So that's roughly here. That's where our first confidence interval was. So it's between these two. Our second confidence interval was between 30.1 and 32.1. So let's put those numbers down. 30.1, that's going to be pretty close to here, and 32.1 here. Nice. So what the problem is getting at and asking you, is there a real difference between these two? There could be, if the true values actually ended up at extremes that were away from each other. But because there's overlap in these confidence intervals, we can't say that one is necessarily different than the other one. So statistically, those are the same. Let's take a look back here. It says, let's see. Are these results very different from the confidence interval with only 18 samples? No, they're not very different. All right, they overlap. So we can't say that there's a real difference between those two confidence intervals. Okay, nice. And that's not example B yet. Let's move on to example B. A data set includes 107 body temperatures of healthy adult humans with a mean of 98.7 and a standard deviation of 0.72 degrees Fahrenheit. Construct a 99% confidence interval estimate of the mean body temperature of all healthy humans. What does the sample suggest about the use of 98.6 as the mean body temperature? All right, so again, like the last one, let's start by writing down a couple things that are relevant. We're going to do this one a different way. We're not going to use the summary statistics that are given. I want you to experience calculating this from the actual data set, which is built into StatDisk. So the only thing I want to notice right now is that we're going to use a 99% confidence interval. That means our level of significance is 0.01, or alpha is 0.01. Let's come up here. Before we do our analysis, we need to get the data. So go to data sets and then 14th edition. Once you're there, data sets, 14th edition, you want body temperatures. So click that one and it should just give you all kinds of data, more than you want to look at. We wanted a 99% confidence interval, so we're going to have to change that. But before I change that, there's one other thing I want to change. Does anyone see what that would be?
Sample size.
We'll let StatDist take care of that, because I don't know how many are in this column. You're going to have to click Use Data. Because we're no longer going to feed in the summary statistics. We're going to let StatDist calculate the summary statistics and then use them. So a lot of work's going to be done kind of behind the scenes for you. Your work has gotten a lot simpler in a lot of ways. Just got to change the confidence level, and it's up to you. Do you want to use the 8 a.m. temperatures or the, I assume that's 12 p.m. I hope they're not doing temperatures at midnight, but maybe they are. I don't know. Do you want to use columns 3 or 4 for this example? 3 it is. Good choice. So, column containing your data, that's going to be day 1 at 8 a.m. We don't know what sigma is. I mean, that would be weird if we knew what the standard deviation was, but somehow didn't know what the population mean was. When you're ready, click Evaluate. Now, I may have gone through some of that kind of fast. So if you didn't keep up at some point, tell me where you're at, and I'll get you here. Are we all here? Can I see from my Zoomers? Give me a thumbs up. Victoria, maybe turn on a camera so I can see a thumbs up. Elijah, same well. All right. How about here? Thumbs up. Doing good? All right. Johnny? All right, well, there's our confidence interval. It's 97.8 to 98.5 if we round it to the nearest hundredth. So our confidence interval is between 97.8 less than mu is less than 98.5. So, okay. Let's state our confidence interval in words. What's that going to be like in words? Why don't you try and write that down in words and see if you want to match what I've got. So I'm going to take this away and write it off camera. Someone want to give it a shot. I mean, if you get it wrong here, it costs you nothing, and you'll probably learn a lot more than you would if you don't get it wrong. Cam? Okay. Tell you what, we got somebody on Zoom. Go ahead. Imran? Yeah, that sounds good. Cam, you want to run yours by us as well? Same thing? All right, nice. I wrote pretty much the same thing as well. We can be 99% confident that the true mean body temperature of healthy adults is between 97.8 and 98.5 degrees Fahrenheit. Now, they do ask kind of a little follow-up question. Are we okay with this far? Things this far? All right, thank you. I do like true mean. You mentioned something that the mean of the population. That's kind of getting at the same thing. Basically, by true mean, I mean parameter. So true mean, or you said the mean of the population, again, that's really getting at the fact that it's a parameter. So I was okay with the way you stated it. I am generally happiest to see the word true here. And then the other thing that I want to see is a description of what that is. It's the body temperature of healthy adults. So 3 things I'll be looking for, maybe 4 things. A statement of the level of confidence, the true parameter, whatever that is. It could be the mean, it could be standard deviation, it could be the proportion, a description of what that parameter is in words, and then of course, the actual range there. So I am pretty particular about that, but there's good reasons for that. Now, let's take a look at something else. I don't know about you, but I've always associated the average human body temperature as being 98.6. That was the average. But that's a little bit misleading. So let me give you a little bit of history behind some of this stuff. Of course, in the United States, we're on the imperial system, or the English system, whatever you want to call it. And so we use degrees Fahrenheit, which of all the units in the English system, degrees Fahrenheit, I like the best because on a day like today, when it's snowing out, it would be below 0 on the Celsius scale. But for us, it's like it's in the 20s, all right? But it'd be negative in Celsius. And it just bothers me to think of it as being negative. In any case, that 98.6, I don't know. That sounds pretty precise, right? 98.6. But that 0.6 is kind of a little bit of a misleading. The way you get that 0.6 is the original study to do this was done in Germany over 100 years ago. And some German physician measured the body temperature of it was between 20 and 40,000. I don't remember the exact number. It was 20,000 patients doing that by hand. That just looks awful. And he found that the average body temperature was 37 degrees, but that's Celsius. What happens if you convert that to Fahrenheit? Well, multiply by 1.8 and then add 32. That's where your 98.6 comes from. Now, it didn't have that level of accuracy in Celsius, but it does in Fahrenheit. So it seems to imply more accuracy than really it should. Well, what do we see when we look at our confidence interval? We cast a wide net. We're a 99% confidence interval. That's pretty good. What's that saying about our confidence in this? Does it look like the human body temperature, average human body temperature is 98.6? No. It's probably somewhere between here and here. Now that's going to change depending on if you're male or female, time of day. There's a lot of variables that do this. I mean, during the height of the pandemic, when everyone was checking your forehead, I would always make a game out of making predictions. I tended to come in around 97.3 was my guess. But it was just kind of funny to go up and say, 97.3, and they check it and they're like, wow, this guy's good. All right, so here's your confidence interval. It falls outside that confidence interval. So, okay, we don't think that this is actually correct, and it's probably not. Okay, let's keep going. Example C. clinical trials conducted to test the effectiveness of a drug for treating insomnia in older patients. Before the treatment, 23 subjects had a mean wait time of 104 minutes. After the treatment, the 23 subjects had a mean wait time of 81.3 minutes and a standard deviation of 22.7 minutes. Now, if you're looking very carefully, the before treatment, they just told you had the 23 subjects and they told you what the mean is. So they're not giving you much information about what happened beforehand, but afterwards, that's where they're giving you the information. So with example C, let's start out by writing down the information, starting here with 23 subjects, a mean wait time of 81.3. Example C. So N was 23. The mean wake time was 81.3, and the standard deviation of that wake time was what, 22.7? Let's just look back here. Yeah, 22.7. That's a pretty big standard deviation for these numbers. 22.7. We wanted a 95% confidence interval. All right, that's most of what we want to know. Let's see if we can't figure out what that confidence interval is going to look like. Now, you shouldn't really have to go anywhere. You should already be at the confidence interval, but just to give you some more practice in finding that, it's analysis, confidence intervals, mean, one sample. You want to be 95% confident, that's good. What should I put in for my sample size? 23, beautiful. Then sample mean was 81.3, standard deviation. Where should I put the standard deviation? First one or second one?
First one.
First one, because it's a sample standard deviation, 22.7. And evaluate. Nice. So our confidence interval is between 71.5, we'll call it, 71.5 to 91.1. I'm rounding it to a more sane 1/10 because I don't think we really need to keep track of things down to a 100,000th of a minute. Seems a little bit excessive. So like that. Gabby, what should I put in between this? What symbol is going to go there? Yeah, the M. What's our Greek letter M called? Mu. Yes, mu. Thank you. Now, this is one way you can write your confidence interval. Another way you can write your confidence interval would be this. You could do X bar plus or minus E. Now, in our case, X bar was 81.3. Does anyone know where I can pick up E without doing too much work?
Right above.
Yeah, right here. E is about 9.81. So, okay, great. Now, if you had this, if you add 9.81, you'll get about this. If you subtract 9.81, you get about that. So that's where these numbers are coming from. This number comes from that formula that I showed you earlier. I think it was in response to Cam's question right there. You're not going to have to calculate that directly, but we are going to have to interpret this. So write a sentence that interprets that confidence interval. So while you do that, I'm going to do likewise. So grab what you need from here because I'm going to pull this off. Okay. Who wants to give theirs a try? Esther?
We can be 95% confident that the true mean wait time for people with drug treatments is between 71.5 and 91.1 minutes.
Beautiful. Did you want to try yours too?
I had basically the same thing, I just put we can be 95% confident that the true mean wait time for a population with treatment is between 71.5 and 91.1 minutes.
Nice. Yeah, looking good. Both of them. Both of them. All right, thank you, ladies. Let's take a look at a graph of this. And that's going to go down to 71.5, and then over here we have 91.1, and up here we've got the before time, before this experiment was done. Before wake time was 104, so 104.0. So here's your confidence interval. Does it appear to have changed the mean wake time?
Yes.
Yeah, it really does. So, you know, it'd be fair to conclude that it appears as though the treatment is effective because we've shifted the bar. It no longer overlaps 104. It's significantly different than that value, so it does look like the treatment is effective. So that would be your conclusion for the last part here. It says the confidence interval does not include the mean wake time of 104.0 minutes before the treatment. So this means the before and after treatment are different. The results suggest the treatment has a significant effect. So beautiful. All right. We'll talk about wait time in a little bit. When we finish this section, we talk about it relative to, I don't know, daylight savings time, which is messing with everyone's biological clock at the moment. On to example D. Oh, and this one's got some data, so let me put the data in to D2L for us. And then you can pull it off of D2L. So let me just copy this here. Copy that. And I'm actually going to paste it into StatDisk, because sometimes when I paste it directly from something to StatDisk, sometimes when I paste it to D2L, it doesn't paste correctly. So let me copy it from here and put it in StatDisk, or put it on D2L, I should say. So it'll be in the announcement sections. Boy, I hope this goes in for you guys okay. Data. If it doesn't go in for you, let me know. I'll see if I can't do something else. But I'm hoping that it'll paste in directly. Does it? All right, let me try this again, because I don't want it to skip spaces. Yeah, I was worried about that. Let me try this again. Edit. There we go. I think that one will work. Try that one. Copy that over to StatDisk. That should work. While you're working on that, let's acquaint ourselves with problem D. Listed below are student evaluation ratings of courses where a rating of 5 is excellent. The ratings were obtained for a university in in some unknown state. Construct a confidence interval using a 95% confidence level. What does the confidence interval tell you about the population of all college students in the state? All right, so let's see. We're in a 95% confidence interval. And that's really all that we're going to write down from right now, because we're going to let StatDisk do a lot of the rest of the heavy lifting for us. So this is example D. %95 confidence level. Someone remind me where we got to go here. Chloe, thank you. Where do I got to go to do this analysis? I've got my data in, but need to find out where I got to go.
To find, are we trying to find the
Confidence interval, yeah.
Go to analysis
Analysis,
and confident intervals
Hmm.
and then mean or
there's 3 means. Which one?
one.
Mean, 1 sample, good. We will get to the other 2. There's also something else I need to do before I get going. Philo, remember that? What else do I got to do before I get going on this one? Talking on StatDisk, right here.
Standard deviation.
You got some help from the chat here. Want to click use data, because we actually have the data. We're not going to be feeding in summary statistics. We actually have the data. So we'll use data, select column 1. We don't know what the population standard deviation is. That's okay. We didn't expect that. That would actually lead us to a Z distribution. That would be something like this. If we had, and we don't know that we have, but if we had normally distributed data and we knew what sigma is, then StatDisk would be programmed to actually use the Z distribution. But you should not really end up there. It will make a difference to your answers, so make sure that you put this in the right spot, or that you don't put in the standard deviation, the population standard deviation. It's column 1, click evaluate. Bam, there we go. Our 95% confidence interval population is between 3.71 and 4.16, we'll call it. So 3.71 is less than mu, is less than 4.16. You know, let's keep the margin of error around. It's kind of an interesting thing to look at. E is 0.223, we'll call it. That's our margin of error. The one thing I really don't like about this is the fact that they didn't actually tell us what X bar was, did they? X bar is your best guess for what this is. So you could go back and make StatDisk calculate your mean for you. That's okay. But, you know, there's an easier way to get X bar. Or there's another way to get X bar. I don't know if you regard it as easier or not. Anyone want to guess? So our confidence interval looks like this. This is really X bar minus E. This is X bar plus E. X bar is going to be directly in the middle. So if I want to figure out what X bar is, all I have to do is average those two. So add them together, you get 3.87 and divide by 2. That should be your X bar. Yes?
Couldn't you also find X bar just by like taking one, subtracting E or adding E?
Yeah, you could take this and subtract E, or you could take this and add E. Yeah, that'd be another way to get it. Or you could take and subtract those and add these, divide by 2, or I just did that one. But yeah, there's probably a lot of ways. You could also just go back to data and then do explore data descriptive statistics and let it do it stuff. So there you go, 3.93. This is a lot of ways you can get X bar. It's just for whatever reason, they don't actually give it to you as part of the output of your confidence interval. So ours ended up a little different than what they have here, but I think this is a different data set than what's here. At least that's the way it copied. There's a follow-up question. Let's state this confidence interval in words. We can be blank percent confident. In this case, it's 95% confident. And then try and finish it off yourself. Practice it here. Test yourself now while there's no consequence. And if you're curious, if you want to look back, here's the actual problem. Does anyone want to test theirs out? Yeah, Victoria, give it a shot. Nice, nice. Anyone else want to try theirs out? Yeah, go ahead. Yeah, sounds good as well. Nice, thank you. So there is some variety in the way you can write this, and yeah, I'll just look at it. Again, I'm looking for certain elements like you have the percentage confidence interval, you're talking about the population parameter, you can express that by saying true mean, you describe what that mean is, and then you give the range. So hopefully something that you're getting pretty good at. Yes. I think that they had a different data set here. So when I copy this out of my stat lab, it's always giving me a new problem every time I go to it. So when I copied it, I probably got a different data set than was represented here. Yeah, you're right. What we got doesn't match what they had here. But I'm not worried about that. I think what we've done for the problem is correct. All right, it's just that they had different data is all. But thanks for asking about that. There's a part B here. What does this confidence interval tell you about the population of all college students in the state? What do you think? Does it tell us anything about the rest of the state?
No.
Got an answer of no? Anyone think we can generalize this? No, I don't think so. We don't know how representative this college is or isn't of the state as a whole. So maybe it is, maybe it's not, but we just don't know. We can't generalize it. So that's it. That's all we'll do with that one. So the confidence interval tells you nothing about other state schools because they weren't in the sample. And I guess more to the point, we don't we don't know how representative this state school is of the other colleges in the state, so no, it's just not gonna happen. Okay. Let's go to our next example, and this one's already kind of done for us. At least, you know, a lot of the heavy lifting. And that is, we've got data from 2 different restaurants. It leads to 2 different confidence intervals. So example E, we got these 2 different confidence intervals. One of them is for restaurant X and one of them is for restaurant Y. I don't want to call them restaurant X and restaurant Y, so we'll call it Burger King and Arby's. All right, so BK has a confidence interval for their serving times of between 164.7 and 194.5 seconds. So a little bit less than 3 minutes to a little bit over 3 minutes. So 164.7, less than mu, less than 194.5. Choking on this part here. It should be 194.5. And for Arby's, that was between 142.1 and 165.8. Okay. Let's graph each of these. Put them on a number line and graph them. So let's see. Okay. I just had to make sure I had a good enough scale here. So I'll do 140 here, 150, 160, 170, 180, and 190. So we'll graph Burger King in pink. So Burger King's average server time is probably somewhere between these 2 numbers, between say 164.7 and 194.5. So somewhere in there, that's where Burger King is. And how about Arby's? Arby's has got serving times somewhere between 142.1 and 165.8. And let me label these up here. That's 164.7 and 194.5. Arby's will do in orange. And that's somewhere between 142.1, so it's way down here, up to say 165.8. So the big question that you're going to be asked here is to compare the results and then make a conclusion. So you've got 3 choices. The confidence intervals for the estimates for the two restaurants do not overlap, so it appears restaurant X has a faster mean service time than restaurant Y, so that would be Arby's is faster than Burger King. Or the confidence intervals for the two restaurants do not overlap, so there does not appear to be a significant difference between the mean dinner times at the two restaurants. Or finally, the confidence intervals overlap so that there does not appear to be a significant difference between the mean dinner times at the two restaurants. So let's get one thing straight first. Do the confidence intervals overlap? Yeah, just a little bit, but they overlap right here. Overlap. And that's enough. So it could mean that the mean wait time at Arby's is at the high end. The mean wait time for Burger King is at the low end of their respective confidence intervals, and they overlap, so that there's really no difference between the two. And that's your conclusion, is that statistically we can't say that there's a significant difference. So of the three things on your handout, we're going to conclude the last of them. So go into your handout. This should be your conclusion. Let's see, is this the right one? Yeah. E. Thank you. So it says the confidence intervals estimates for the two restaurants overlap, so there does not appear to be a significant difference between the mean dining times at the two restaurants. That's your conclusion. So we didn't miss it by much. I mean, it's close, but there is an overlap, so we can't conclude that one is different than the other ones. Now, if you wanted to make that confidence interval smaller so that you could find a difference, one thing you could do is increase the sample size. That's going to tend to make the confidence interval smaller. All right. So that's what I wanted to get at example E. We're going to do one last one. It's going to be example G, and then we'll call it a day on this one. Are we okay with example E? Let's move up to example G. And let me bring you back over here. Samples of DNA are collected, and the four bases of A, G, C, and T are coded as 1, 2, 3, 4, respectively. Who remembers their anatomy from high school? A, G, C, and T. Remember what those stand for? Adenine, guanine, cytosine, and thymine. Four bases. All right. Anyways, they're coded, and this is the data. Now, we're not going to bother trying to get the confidence interval. Those are just the numbers here. I'm more worried about the conclusion to this. What's the practical use of the confidence interval? Select the correct choice below. If need be, fill in the boxes to complete your answers. Well, I'm not going to worry about the exact numbers. All right, but I am going to worry about, well, what does this mean? So here's your three choices. Try and pick which one you think looks best for this data set. And that should be a C, not an A. I don't know how that keeps on getting changed back to an A. It's a C. I believe it's C on your sheet. Folks on Zoom, please put something in the chat as to one of your guesses. If you're here, turn to a neighbor and see if you're on the same page. Which ones of these do you think works best? Convince your neighbor that you're right.
Jeff, sorry, I have to leave everything here and go blow my nose from the side.
Yellow, yellow. All right, I don't hear too much discussion. You guys confident?
No, I'm thinking about it.
No?
I'm not confident in my answer,
Me
so.
neither.
Not confident? So what's it coming down between?
See,
C? A lot of people in my morning class chose A. Before we even get down to there, let's just try and ask a little more basic question. Let's see what we got on the chat here. So these numbers 1, 2, 3, and 4 actually represent names. Does it make sense to average a bunch of names? No. So are our conclusions based on averaging a bunch of numbers which actually represent names? Is that going to really mean anything? So which answer does that correspond to? A, B, or I don't know why that keeps on going back to this.
I also don't know what it means between actors, volunteers, and volunteers.
Oh, it's just because we didn't calculate the actual numbers.
Oh, yeah.
Yeah, I didn't fill in those blanks because I didn't want to bother taking the time to plug in the data. That doesn't really matter because the data are really irrelevant in this case. It doesn't make sense to average a bunch of names, which is essentially what you're doing. So the answer is C. The given numbers are just substitutes for the 4 DNA base names. So the numbers do not measure or count anything. They're a nominal level of measurement. The confidence interval has no practical use. So the correct answer in this one is C. Yay. Okay, comments or questions on this one? All right, I think that's a wrap for section 7.2. Good luck with this in the homework. Please keep up with it.